Hello everyone, my name is Omar Shehab. I'm a staff research scientist at IBM Quantum Computational Science Group. Today we'll be talking about variational quantum eigensolver. This is a near-term quantum algorithm specifically designed to take advantage of a shallow quantum circuit and a noise level. So this is the outline for today's session. So first we are going to give a high-level description of the algorithm. Then we will discuss the theoretical framework for that and when and why this algorithm performs correctly. Finally, I will walk through a sample code about how to use Qiskit to implement the algorithm. So I'm going to start with kind of a recap of what you have already learned from this school. So I'm sure in one of some of the previous sessions you have learned about quantum phase estimation algorithm and its variants. So that's exactly the circuit you are looking at right now. So on the left hand side, this is the circuit for original quantum phase estimation algorithm. As you can see, time flies from left to right, so you start with some initial state which is ket 0, and then you apply layer of Hadamard gate to create an equal superposition of all basis states. Then you run controlled unitary. So basically the goal is to estimate the eigenvalue of that unitary, and you apply that unitary in a controlled manner, and the control register is the top register. Then finally you apply inverse quantum Fourier transform, and then you measure, right? And if you're applying this circuit, say for example, to approximate eigenvalues, you basically read out the binary representation of that eigenvalue from the top register, which is of length t on the left hand side of the screen. So there are multiple variants of phase estimation circuit. One of the most used version is iterative quantum phase estimation, which was also part of this summer school. And the circuit on the right hand side is for that algorithm. So the theory of the circuit is exactly the same, although there are some nuances about performance and complexity analysis. But the main point here is that we reduce the t qubit control register into just 1 qubit, and we basically read out the eigenvalue, the binary representation of the eigenvalue 1 bit at a time from the top qubit. The bottom register is actually the same as the original phase estimation algorithm. So these are the two major variants, but there are also some other variants. The common aspect for both variants is basically the depth of the subcircuit in the bottom register. So as you can see, the depth, there are many assumptions which impact the depth, but one of the requirement is the precision of the result, right? Precision of the eigenvalue your application of interest need. And that will control the power of the unitary you're going to apply. So if you need t precision, the of course the first unitary will have power 2 to the power t, and so the circuit will be deeper if you need higher precision. So and when the depth goes beyond the coherence time, that's where you know that you cannot really apply this algorithm without error correcting code. So that's why we call this as a fault tolerant quantum algorithm. So the question is there a way around it? So way around it means here, can we solve the same problem using a shallower quantum circuit? If we want to do it exactly, no, there is none, but we can get close to that. So that's where variational algorithms are relevant. So VQE, which is the acronym for Variational Quantum Eigensolver, and when people talk about near-term algorithms, there are two very well-known algorithms. One is variational quantum eigensolver algorithm. Another one is QAOA, which is quantum approximate optimization algorithm. Honestly, my opinion is that we have two different names for almost the same algorithm only because they came out from different groups. But operationally, they are same. The theoretical analysis of both algorithms are also same. So if you know VQE, you basically also understand both the theory and application of QAOA. So what are we trying to do here? We are trying to minimize the energy of a system. So, and there are so many applications where you basically solve this problem in some way or other. For example, let's say you want to calculate the binding energy of deuteron. So what you're going to do is you will start with a fermionic model of that deuteron nucleus. Then you will map it to a qubit Hamiltonian using some kind of mapping. And then you calculate the minimum energy or global optima of the energy landscape. So basically, which means that if you have a problem like where you have to calculate the binding energy of some kind of nucleus, yeah, maybe you can use VQE. You can also use quantum phase estimation, but we are talking about near-term algorithms now. Similarly, let's say you have a certain molecule and you want to understand the ground state energy of that molecule. You can use VQE. Let's now think about something which is not a natural science simulation problem. Let's say you want to solve an optimization problem. So you want to find, ideally you would like to find a global minima of the solution, but if not, you would like to find the best local minima possible, right? Sometimes that optimization problem could be a maximization problem, but you could always put a negative sign in front of the cost function and it becomes a minimization problem, and then you can use the existing tools. So for this kind of setup, you can definitely use VQE algorithm. So it is a hybrid quantum algorithm, which means there is a classical part and there is a quantum part. And on the screen, the yellow box is the classical part, and the blue box is the quantum part. So we start with a cost function. So which, if you are solving natural science simulation problem, maybe ground state energy estimation, you basically, your Hamiltonian is the cost function. And on the other side, if you're solving some kind of optimization or operations research problem, your objective function is your cost function. So how do you evaluate the cost function? You basically run a quantum circuit, which is parametrized. And for a given set of parameters, you calculate the cost. Now, there is a classical outer loop, which basically runs the circuit again and again, and at every iteration, it basically perturbs the parameters, changes the value of the parameter, and it checks the new cost or evaluate the cost function again. Let's say we are doing minimization, so if your cost is lower, you keep those parameters throughout the previous set of parameters, and you keep doing that up to your compute budget. So here, theta is basically the set of those parameters, and so traditionally when you construct a quantum circuit, parametrized quantum circuit, we basically use arbitrary rotations as the parametrized gate. It could be single qubit or multi-qubit parametrized gate. So those angles are basically real numbers up to mod 2 pi or pi, or mod pi or 2 pi. So you take those, so the cost function basically takes those parameters and spits out a real number, right? So that's the map here. And so on the classical side, you can use any stochastic optimizer of your interest. Traditionally, we have seen certain optimizers behave well on software simulator of quantum computer, and some other optimizers behave better for actual quantum hardware. We can talk about that in details later. All right. So as I mentioned, this blue box is basically the quantum computer. So you are running quantum circuit. You initialize a state, you run the quantum circuit, parametrized quantum circuit, and your classical outer loop basically runs that circuit again and again. So as I mentioned before, we start with defining the cost function, and it is also known as Hamiltonian because here we are using the language of quantum mechanics. So what is a Hamiltonian? It basically contains all information about the system, right? That's the Hamiltonian. So, and if you have a given state, you can basically, so as you see, so the state could be psi. So the computation, bra psi, h, ket psi actually gives you the energy, right? So it is also known as expectation value. And our goal is to find the minimum energy of that Hamiltonian. So if you think about eigenvalues as a spectrum, you want to the lower energy. So it's a minimization problem. And once you and it's a minimization problem over the parameters. And once you minimize it, you get the lowest eigenvalue. So sometimes you will see this term trial state. So basically, when you are searching a minima in an energy landscape, your probability of success is basically partially determined by your starting point. So if it is a very smooth energy landscape, or if it is a very smooth search landscape, then it doesn't matter where you start from, you will always end up with at global minima after a few iterations. But what if the state is very rugged? So when the state is very rugged, you might end up get stuck at a local minima, and then your outer classical stochastic optimizer may not be good enough or robust enough to actually get you out of that local minima and push you to a lower energy basin. So it happens in classical optimizers for classical optimizers all the time, and it could also happen for quantum optimizers. So that's why choosing the right initial state is actually very important. And we'll not, for practical problems, we will not always be able to find the initial state because it by itself could be a hard problem or could take a deeper circuit. But this is an important part of the algorithm. All right. So now, this VQE algorithm is basically you are basically doing a random walk in a energy scale or a solution space, right? So you will never be able to explore the full energy space or search space. You will always be able to explore only a subset of that space, and there is no guarantee that that subspace contains the actual global minima. So this is something we'd like to understand. One other thing is relevant, so which is also clear from the circuit on the right hand side. So in this circuit, we basically start. So it says it's basically taken from a paper which I believe was used to estimate the ground state energy of lithium hydride. So on the left hand side, you have it's a 6-qubit circuit, and you start with ket 0. Then you apply a layer of single qubit gate, those are the U gates, and they're parametrized. And then you apply a layer of entangler, which are basically you could imagine as a ladder of 2 qubit gates or some kind of linear or some other combination of 2 qubit gate, which basically creates maximal entanglement. And then you basically add another layer of single qubit gate. So layers of 2 qubit gate, a layer of single qubit gate, and you basically repeat that layer as many times as you need. Then finally, you apply a single layer of X or Y gate. So let me explain what is happening here. Traditionally, if you want to start with a layer of single qubit gate, let's say those are Hadamard gate, your intention is basically to create an equal superposition of all possible solutions. And that's okay. In some cases, actually, starting with maximal entangled state might give you some theoretical advantage. So then you apply layers of these 2 qubit and single qubit gate, right? As you increase the number of layers, excuse me, you basically are increasing your probability to explore a larger part of the Hilbert space, which is good because that means that you are increasing the chance of finding the global minima. And the last layer of X or Y gate is basically a layer which makes sure that for any given solution, you're also checking if its complement is also a solution. Let's say your current candidate solution, the bit string representation of your current candidate solution is 0, 1, 0. So the last layer also makes sure that you are checking 1, 0, 1. So it's complement. So because sometimes there are symmetric solutions. So going back to the middle layer, as you increase the repetition of that layer, these 2 qubit gates and single qubit gate, you have to keep in mind that every time you add a parametrized gate, you now have one additional parameter you have to keep track of in your classical optimizer. So there is we are thinking we are solving a quantum search problem with the help of a classical optimizer where we are changing the parameters classically. So if you increase the number of parameters by increasing the number of layers, you're basically every time you add a new parameter, you're increasing the size of the haystack to find the same needle. So you have to find a good balance of how much you want to increase the search space, and which is basically increasing the layer, and at the same time how much of the part of the Hilbert space you would like to explore. So there is no one solutions. You just have to experimentally try which combination works for you. One other comment is, as you increase the repetition of the middle layer, you might also at some point reach the coherence time, because more gates means longer time to run the circuit. So, and beyond that, you basically, every time you add a new gate, you will accumulate noise. So here there are like multiple knobs you have to think about. One is the depth of the circuit, and another one is the noise rate, and also the number of parameters you are going to handle classically. All right. Okay. So the good news here is that thanks to variational principle, we are guaranteed to stay within our global minima. So you might end up finding a local minima, which is probably close to global minima, but not the exact correct answer. But as you variationally search for the solution, you will never go below the global minima, which will be an incorrect answer. So the variational principle basically guarantees the correctness of the approximation. All right. So let's now think about the cost function, like how it can be broken down. So basically, when you execute the VQE algorithm, every time you run the circuit, you basically starts with a new set of parameters, right? They are going to be plugged into the angles. So you, with those parameters, you plug those parameters into the circuit, then you compile the circuit for a target device. So for example, in your original circuit, you have some combination of CNOT gate and other single qubit gates, it has to be compiled and transpiled into a hardware-friendly description, right? Hardware-friendly gates. So we'll do that. So that is typically basically a open chasm list of gates. Then you basically generate microwave pulses based on the circuit, and those pulses go to the quantum computer. It executes the circuit there, and once the circuit is circuit finishes running, you measure it. So now you have a histogram of results, and then you calculate the expectation value. So and every time you start with a new set of parameter and do the same thing. Right. So now sometimes you do some additional steps to do that. So for example, let's say you have a Hamiltonian where there are a bunch of x terms, a bunch of y terms, a bunch of z terms. So when I say a bunch of x terms, it means that x terms of different orders. It could be just one x term. So basically, you are measuring a single qubit. It could be an x term. So you are basically measuring the correlation of two qubits. It could be a three local term like xxx. So now you're measuring the correlation of three qubits, right? And same thing can happen for y or z. In general, if you think about the original variational quantum Eigensolver algorithm, you have this Hamiltonian, which is basically a bunch of x, y, and z term. For each term, you run the circuit. You measure based on that term, and you store the result. You do this for each of the term. Then for each term, you multiply the correlation expectation value with its coefficient. Then you sum it up. That's your result. However, there is a concept of polygrouping. So let's say you have one x term and one xx term. What you could do, and acting on the same set of qubit pair. So what you could do, you could run the circuit only once and measure measure both qubits. Then from both qubits, you can already get the expectation value for the xx term, but you could also do classical post-processing to extract the subspace for the related subspace for the single x term, and then calculate the expectation value from there. So we basically reduced the total number of circuit run by half, because we basically ran it for the xx term. Since it contains the subspace for single x term, we'll just post-process it classically. So this is known as polygrouping. So when you do use polygrouping, you basically, for a general Hamiltonian, you basically run the circuit 3 times, one for x measurement in x basis, one for measurement in y basis, and one for measurement in z basis. So 3 times you have all the result for all the qubits. Then for terms where they have lower orders, you just post-process and calculate the subspace. We'll see example later. If you are solving the QAOA algorithm, which is quantum approximate optimization algorithm, and for just some classical optimization problem in its original form. So traditionally, you will see there are only z interactions. There is z terms. There is no x or y terms, which means that you will only run the circuit, or you will only measure the circuit in z basis, and then do all the post-processing for different order of z terms. All right. Okay. So why this circuit is interesting? Why this algorithm is interesting? So there are reasons. There are multiple reasons. So first of all, it allows you to have an additional knob for the depth of the circuit, control knob to, for the depth of the circuit, and you can make the circuit as shallow as you want. So for example, let me quickly go back to this circuit. So you will probably keep the first single qubit gate layer in its place, and the last single qubit gate layer in its place. But you can still control how many times you'd like to repeat the middle layer, right? The multiple qubit, 2-qubit gate layer and the single qubit layer. So of course, if you have a shallower circuit, you might be sacrificing the accuracy, but still you can make a conscious decisions based on the noise level of your hardware and keep it shorter, so they can at least have some meaningful result. So that's why this VQA algorithm is known as near-term quantum algorithm. The results are basically an approximation of the ground state. So as long as you have an upper bound on how bad it is, and also the upper bound on the variance of that result, you have a way to explain the quality of the result. And finally, it is robust to coherent and incoherent noise. So I mean, understanding the noise for quantum hardware itself is a whole field, but in general, say coherent, you could imagine coherent noise as like over rotation or under rotation of the angles in the parametrized gate you will be using. So so if the gates are not perfect, which is true, and there's some over or under rotation, you will still find the lowest energy or something close to that energy, but maybe for a slightly different set of parameters. And your goal is not to find the parameters, is to find the solution. So as long as you find the right solution, if those solutions are skewed towards a slightly wrong set of parameters, you're fine. So that's called robustness to coherent noise. For incoherent noise, to some extent, it's not like foolproof, but of course, since you have all these kind of parameters or maybe hyperparameters, you can basically take advantage of that to find the solution. And but also, the algorithm is not foolproof to noise. That's why there is this whole field of noise mitigation, which you will learn in future sessions, where you can actually improve the result of variational quantum eigensolver algorithms. So what is a traditional workflow, typical workflow for the VQE algorithm? As I mentioned, in this algorithm, this is a hybrid algorithm. So you have a quantum circuit being run by a classical stochastic optimizer, which is an outer loop. So of course, one of the things you can start with is what optimizer you're going to use, and probably you will make decisions based on your experience. So for example, when I run problems on a hardware, I typically choose SPSA optimizer, which is I think stochastic perturbation. I forgot the full name. So it's very well known as a SPSA optimizer, which performs reasonably well on noisy hardware. When I'm using quantum simulator, it's software simulator, I stick to Kobila. It performs there well. So basically, I use Kobila to check if my code is correct. Then I move to hardware with SPSA optimizer. So choice of optimizer is one of the earliest steps. Then the second step is Hamiltonian mapping. Basically, you start with the cost function defined in the terms of your application domain. So if it is natural science simulation problem, you have maybe some fermionic Hamiltonian. If you are working on an operations research problem, it will be defined in terms of computational basis, like a bunch of z terms in that Hamiltonian. Then you map that problem Hamiltonian to a qubit Hamiltonian and optimize or reduce it as much as possible. So there are multiple ways you can actually do this mapping. So for natural science like chemistry or physics problems, you typically start with fermionic Hamiltonian, then you do some kind of mapping to map it to a qubit Hamiltonian, and Qiskit currently supports Jordan-Wigner mapping, Bravik-Kitaev mapping, parity mapping, and there are people are investigating a bunch of other mappings. Sometimes they could be aware of the device hardware. So that's the whole field, research field. And for classical problems, even if you don't map it to a qubit Hamiltonian because they are already in a qubit Hamiltonian formulation, you could still do some kind of reduction. So for example, Qiskit supports circuit knitting or wire cutting techniques. There are also other approaches. Maybe you can pick a Hamiltonian term, then you back calculate the causal cone or light cone for that Hamiltonian, which is basically a sub-circuit that impacts the expectation value, and you stick to that sub-circuit. Don't run the whole Hamiltonian. So there are ways you can actually reduce the Hamiltonian. And once you have the final optimized reduced Hamiltonian, now you decide what kind of variational form you are going to use. So here variational form means basically the circuit or answers you are going to use, and how you are going to parameterize it, and what initial state you will start with. So traditionally you will start with ket 0, then you will probably create an equal superposition, then you will apply a parameterized circuit. But there are actually different variations. For example, there is a concept of warm start, where you basically have some understanding about the structure of the problem space, and that creates a bias towards a certain solution subspace, and you want to construct your circuit so that it is biased towards that subspace. That's a warm start approach. Finally, there is a level hardware control. Basically, if you know anything about the hardware, you may want to take advantage of that. So for example, let's say you know certain parametrized gate performs on the hardware better than other set of parametrized gates. So you may want to create a circuit so that you can take advantage of that knowledge. Finally, and this will be covered in a separate set of sessions, you could have your classic outcome, which is basically a classical set of results from your quantum circuit, and you use all kind of error mitigation technique to improve that result. So there are M3 error mitigation, zero noise extrapolation, probabilistic error cancellation, different types of error mitigation technique you could use to improve the quality of the expectation value. So as I mentioned, like there are two very broad area of applications. Chemistry here means chemistry / natural science, where you can estimate the ground state of a nucleus or of a molecule. You could also study excited state by change the algorithm a little bit. But as you see, this is the algorithm which basically give you access to different energy levels. So, it's a very suitable near-term algorithm for such problems. For operations research or optimization problem, the list I have here is more like canonical problem, but you could also use the exact same algorithm, let's say for a more practical problem, let's say mixed integer programming problem or some kind of satisfiability problems. You basically take the problem, express it as a qubit Hamiltonian, and then use a parametrized circuit to find the minima or maxima of that, to approximate the minima or maxima of that qubit Hamiltonian. So, it's a natural question. So now that we know how this algorithm works, it's a natural question like, what is the computational complexity of VQE? So here, computational complexity means traditionally, if we speak the language of theoretical computer science, you basically want to know the time, space, and sample complexity of an algorithm. Time complexity means how long does it take to run. When it is quantum algorithm, it can be translated as how many quantum gates you are going to run, because they can be directly mapped to time to run the gate. Then space complexity, traditionally in the language of theoretical computer science, space complexity means the amount of memory you need to run the algorithm. For quantum algorithm, a natural proxy would be number of qubits you need. And then the third one is sample complexity. So in the context of this type of algorithm, one of the measure of complexity is how many times you're actually running that outer loop, and for each loop, how many times you're actually running the short of the quantum circuit. So these two contributes to the sample complexity. So for space complexity, you could already see that in phase estimation algorithm, you had this control register, which is not related to the bottom register where you actually start with implement the problem Hamiltonian. The top control register, which where you read out the eigenvalue, they are not present in the variational quantum algorithm. So you are already saving some qubit when you switch to this algorithm. But it's not going to asymptotically. This saving will not asymptotically scale because the width of that register is basically the requirement on your precision. However, depth-wise, so on the phase estimation problem, you have been using the unitary. You exponentiate the Hamiltonian. You apply the unitary up to different rotation. Here we are not doing that. We kept the circuit construction kind of independent of the problem Hamiltonian. So and we basically hyperparameterize it, and so that we can basically search in a solution space. So when does it actually perform better? We don't know for sure, but there are ways to understand it. So let me show you like how to think about this situation. So when we solve problems in computer science, we have theoretical computer scientists have this habit of creating classes of problems based on their hardness. So for example, you can see different classes like P, polynomial time, BPP, bounded probabilistic polynomial time, BQP, bounded quantum polynomial time, NP, non-deterministic polynomial time, and QMA, quantum Marlin author, right? So these are basically different classes of problems, and they are grouped based on their hardness. So an example of P is going to be, let's say, primality checking. So if you want to know whether a given number is prime or not, that's actually an easy problem for computers. So it's in P. An example of BQP will be prime factorization. So factoring integers into their prime factors is actually easy for quantum computers. That's why it will be in BQP. But we don't know for sure whether it will be in P or outside of P. So it's in a region where P is a subset, but we don't know for sure whether it is in P. NP is basically problems for which finding the solution is hard, but if you find a solution, verifying the solution is actually easy. And it has its quantum version, which is QMA. So when we solve a problem using the variational quantum Eigensolver algorithm, let's see where the problem lies. So first of all, typically the problem is k-local, which means that there are local structures in the problem, and that makes the Hamiltonian a k-local Hamiltonian. So for example, if you are trying to find binding energy of a nucleus, there are local transition between pairs of energy levels. And that probability of that local transition actually creates local structure in your cost function or Hamiltonian. Similarly, let's say you are trying to solve the traveling salesman problem as an optimization problem. The traveling salesman problem is defined over a graph which has local structure. So that creates the locality in the Hamiltonian. And second, so basically it's a positive matrix, right? So and the depth and the iteration is basically polynomial in the size of the input. And the way we define the answers is basically we don't scale the depth of the circuit in the size of the problem, right? So in a sense, it's a constant depth circuit. We fixed now the number of iteration, and once we fix it, we always use that number. So it's a constant depth circuit. And more specifically for IBM quantum hardware, we try to design the circuit in a way that it can be easily mapped to a 2D computer chip, quantum chip. And finally, it's a gapped Hamiltonian problem. So you see all these gaps between the eigenvalues, guaranteed gaps between the energy levels. So the point here is that depending on what problem you're solving with VQE, it could be easy or hard. So if your problem Hamiltonian is a 1D gapped local Hamiltonian problem, it's an easy problem for VQE. But you may not want to solve it with VQE because there could be easy classical options. So anytime you have an easy classical option, you may not want to use quantum computer because it might be hard. When it is between NP and QMA, which is probably the hardest problem here, just general K-local Hamiltonian problem, you may be able to find a solution, but there is no way you can efficiently verify it classically. So there are actually lots of practical problems there. But in lots of cases, you might be in a situation where you are in NP but may not be in BQP. So if somehow you can get an approximate solution with VQE, you can easily verify it. And if you're in BQP, you can still use VQP if the circuit is still not asymptotically deep, but practically deep. You can use VQP. So there are different cases, and the successor probability of VQE for different hardness, different level of hardness could be different. And for some cases, VQE could guarantee success, but you might have a better classical opportunity or better other quantum technique. So there are a bunch of papers, and there are some other papers since these 4 papers have been published, which you can go and check out to understand the theory of this algorithm at a deeper level. So basically, to summarize, it basically extends the reaches of classical technique. Here, classical technique is a stochastic optimizer, but internally there is a quantum routine which lets you to explore Hilbert space. It uses shallow circuits, so sometimes you can actually run them on today's quantum computers. It is robust to noise, and basically there is the workflow of the VQ algorithm involves choice of optimizer, choice of Hamiltonian mapping techniques, choice of initial state, choice of circuit, and choice of error mitigation technique. All these choices contribute to the final success of the algorithm. Now I will go to a web page which is a part of Qiskit textbook, and walk through a code which basically gives a demonstration of this algorithm. All right. So if you're not familiar, this is the website of Qiskit textbook, learn.qiskit.org. I think I should increase the font size a little bit. So there are tons of algorithm demonstration in this book, and you can actually check them from the content. It's a huge number of algorithms. And one of those algorithms is VQE. So this algorithm basically simulates molecules using VQE. I'm not going to walk you through every a step of this implementation or all this text discussion, which will take about an hour. But I will basically describe different blocks of the code and how that connects to what we have learned so far. So which means that I'm not going to read any of this text, just jumping to the code blocks. So, but to some of you this might seem familiar because we actually discussed this in our session today. So first code block is basically starts here. These are standard utility code block because you use a stochastic optimizer. You want to seed your random routine. Then this code basically imports a bunch of qubit class which you use to create the variational form, which is basically the other name for quantum circuit. And So as you can see in the quantum circuit, you're using quantum register, classical register, and a bunch of parametrized gate. And finally, you add measurement. All right. The next phase, you basically define the objective function. And this objective function will be translated into a physical Hamiltonian. Here, you parameterize the classical optimizer. I mentioned that when I use quantum simulator, I stick to Cobila. When I use quantum simulator, quantum hardware, I stick to SPSA. So you see, we are importing Cobila from our optimizer list, but there are others, and you can use any one of them. And we are parameterized it. We are setting an upper value for how many iterations it will go through. So once that part is done, so here in the code we talk about different options for answers or variational forms, and how different circuits are, how we are creating entanglements, how we are parameterizing them, and you have actually a bunch of different options. Feel free to take advantage of those. And so those are like initial discussion. So to use the VQE algorithm, we have to start with importing the VQE class and from Qiskit. Then you basically use get qubit op, which basically takes the problem Hamiltonian and express it as a qubit Hamiltonian. And as I mentioned, we have different options to map harmonic Hamiltonian to qubit Hamiltonian. As you see here, they are using parity mapper, but you could also use Jordan-Wigner or Bravik-Kitaev mapping. Jumping to there, you can always use our Eigensolver to check the correctness for a small scale problem. And this is the example we are using here. And then you can also use some kind of quantum simulator to actually execute the algorithm. In this example, we are using state vector simulator. You could also use chasm simulator, which is actually more stochastic. So once you execute this for the problem, and I believe it is lithium hydride molecule, we basically calculate the ground state energy and dissociation curve here. Yeah, so and in the same example also talks about how to use a noisy simulator. So you will start with the target quantum hardware and create a noise model for that and run the simulator using that noise model, so you can have some estimate like how that noisy hardware will behave. And you can also use the actual hardware using this example. So feel free to check out the link. It is on the last slide of the deck, and run the examples, run on our hardware, and compare your result with your friends and from also with this page. Thank you.